Hi everyone, this is another video about polymer reaction engineering. So far, we have seen that monomers build up polymer chains, and that understanding this process is crucial, since the great variety of polymer properties are determined during the reaction. In fact, we typically refer to polymers as products by process. Now, the focus of this video is answering the question, how are polymer chains formed? Or at least make a first step in that direction. And while we lay the basis to approach this question, we will also touch upon some modeling considerations. Polymerization mechanisms can be divided into two groups: step growth and chain growth polymerizations. These names, step and chain growth, are, in my opinion at least, very elegant to describe, the main mechanisms leading to polymer buildup. Let us start to see why this is the case, or rather why I think these names are very well suited to describe these two types of polymerization, starting with step growth. We said multiple times already that everything starts with the monomers. These are the building blocks of polymers, but now the question becomes, what qualifies a monomer to undergo step growth polymerization? It needs to have functional groups that react with the functional groups of another monomer. For instance, here we have an orange monomer with two functional groups of type A, let's say some acidic groups, some COOH, for instance. We also have the green monomers that has two functional groups. These are B type functional groups. For instance, it could be an amino group, right, NH2. And in our example, A can only react with B, forming a polymer linkage. So in our example, it would be a CONH linkage, but we will just depict it with an L here for linkage, that connects the two monomers. And actually, we already formed a dimer. Now, this reaction might be equilibrium limited. So depending on which monomers participate in their corresponding functional groups, and it might involve the release of a small molecule. Here, R. It could be water, for instance. There are a lot of monomer options out there. Some have type C, type D. We will see more chemistries down the road. Some have two functionalities, some have three, but now we want to focus really on the polymer formation, and for that our example is more than sufficient. So we had at the beginning two monomers with a total of four functional groups, right, 2A and 2B ones, and now we have one dimer, so a polymer chain of length 2 with one linkage, this gray L. The dimer has only two functional groups remaining, 1A and 1B. So what could happen next? We need more monomers to understand this. So let us take now 20 monomers, 10 orange ones and 10 green ones with their corresponding functional groups. So we have 10 orange monomers that bring 20 A functional groups and 10 green monomers with their 20 B functional groups. Say two monomers react with one another, as we said before, and ta-da, we have now one dimer. And we have 9 monomers of each type, since we lost one orange and one green monomer. Now we have a total of 18A and 18B functional groups and one dimer. It's down there. If you don't see it, that's okay. There is only one of them, and this already should put things into perspective. The dimer, of course, could still react. It has 1A and 1B functional group, but what do you think? Is this really likely to happen for the dimer in this scenario to react next? As you might have guessed, the answer is no, right? But why? We know the functional groups mediate the reaction, and our lonely dimer only has 2 of those. The remaining 18 monomers have a total of 36 functional groups. So it's very unlikely that our lonely dimer, the only one we have, reacts with a monomer to form a trimer, so a polymer chain of length 3. It's much more likely that the functional groups of 2 monomers react with one another, forming another dimer. And then there were 2 dimers. But even together now, they only have 4 functional groups, right? So to recap, we have 8 orange monomers left with 16 A functional groups. We have 8 green monomers with 16 B functional groups. And we have now 2 dimers with 2 A and 2 B functional groups, right? So again, it would be more likely for 2 further monomers to react while the dimers remain spectators for now. You get the gist. The reaction occurs in small steps, meaning many monomers first need to react with one another and form a significant number of dimers before these will react with a monomer and form a trimer, so polymer chains again with 3 repeating units. And to see a tetramer, so with 4 repeating units, well, either 2 dimers combine and form a tetramer, or a trimer reacts with a monomer, since, well, 2 plus 2 or 3 plus 1 both give 4. Anyway, let us have here a hypothetical situation to look at when a trimer forms. So now here we have 3 orange monomers, 6 A functional groups. We have 3 green monomers with 6 B functional groups, and we have 7 dimers. So the majority of functional groups are actually on dimers. So it's likely that these will, one of those dimers will react. We could even see a tetramer, in fact, right? Since 2 dimers could react with one another. Alternatively, we would need, many trimers to form and then pick up some monomers. So the step growth mechanism implies, as the wording suggests, that first we need to form short chain polymers that are termed oligomers, and only after a longer time, when these oligomers start to combine, and I would have needed way many more monomers in my sketches, only then longer polymer chains will be formed, because we need a base of these shorter chained oligomers. So one step at a time. Very important note. All species actually do react with all others, or may react with all others, at the same time. It's not that the dimers politely wait on the sidelines for all the monomers to have reacted. All molecules grow at the same time, but some are more likely to do so than others, depending on the relative abundance. Think of our lonely dimer in an ocean of monomers. Now, the key features of step growth polymerizations are 1. Functional groups drive the reaction. In fact, any 2 chains can react if their functional group can. Right? The reaction can be equilibrium limited. That's also something we said. Number 2, all molecules grow at the same time. All are ready. They only need functional groups. The event more likely to occur will involve those species with the higher concentration of functional groups. Again, here remember the lonely dimer in the ocean of monomers. And 3, and this is something which we only indirectly mentioned, but the average chain length increases slowly with functional group conversion. Since, as we saw, we first need to build up many oligomers, so shorter chains. So at the beginning we only have monomers. Then the molecular weight increases to dimers and trimers and such, but we don't have very long chains. This will happen only very late in the reaction when the conversion is almost all done. We will see more later on. But what about chain growth? Let us start with monomers again. What are the features of monomers that grow according to chain growth mechanisms? They possess double bonds, such as carbon-carbon ones. So to visualize these monomers, we will still use spheres, but since we want to capture the reaction process through which these monomers build up a polymer chain, we will draw an equal sign on top of each sphere to represent their unreacted double bond. Here too, many different monomers exist. Some have 1 double bond, others have 2 or more. We will look at them another time. Now, we consider only one type of monomer, let's say blue monomers, with 1 double bond. This could be, for instance, styrene, just to make an example. Now, let's take 30 monomers. Does something happen now that we have 30? Are there 30? There might be 20 here. Anyway, nothing happens. That's the point. Without the presence of an active species, such as a radical or an ion, nothing happens. Doesn't matter if we have 20 or 30 monomers. This is already a very big difference with respect to step growth. There, the reaction could start directly with the monomers, but not here. Okay? So without active species, nothing happens. So let's make something happen. let us add a radical species. Here it is. And since it is very reactive due to its unpaired valence electron, it attacks a double bond. It attacks a double bond, and well, now the fragment is connected to the monomer, and the radical is on this new construct, which is, drum roll, our first polymer chain of length 1. But since the radical is still active, what will it do? Well, you guessed it, probably the same. It will attack another double bond. And now we have a dimer, okay? Of course, we had a dimer also before, right, in the step growth case. But what is the difference here? In step growth, for the dimer to react, we needed much more time. Namely, we needed many more dimers to be there, because that single dimer, well, since the reaction was mediated by functional groups, could not outweigh, let's say, the number of monomers that were there. But here it's completely different, because now here there is only one active site. This active site is on the dimer, so it doesn't matter. Now there are here 28 monomers watching, they're just watching. The one that has the active site is the dimer, and therefore the dimer will react, right? It will find another double bond and consume it, right? So it's species with active sites that control actually the consumption of monomers. So another double bond is consumed, and now the active site is on the trimer, right? So the trimer is king and the merciless attacker of monomers. Okay, this joke is already old, but the point is that the trimer will attack another monomer, and it will form a tetramer with 4 repeating units, so a chain with 4 repeating units. What do the other 26 monomers do? Nothing. They stay there and watch in this example, right? No one else is reacting. And then again, our chain grows, find another a double bond, and forms a pentamer, right? A 5 unit chain. Because of this, let's say that's why it's called chain growth, right? Because a few very high molecular weight chains arise from the very beginning. Sure, here in the interest of time we stopped at a pentamer, but a few thousand monomers could be easily added to one growing chain. Of course, things are much more intricate and fascinating than what our sketch shows. Typically, there are multiple active sites being formed, active sites can terminate, and so much more. But here our focus was to understand the central reaction in chain growth that enables the buildup of polymer chains, which is the so-called propagation reaction. Okay? So the key features of chain growth polymerizations are only chains with active sites, such as radicals or ions, grow. Note that the lifetime of a chain depends on the type of active site, as we will see, right? But this is an important difference with respect to step growth, where any monomer could react. Here it's not the case. You need an active site. Also, many other reactions occur. In fact, for chain growth to occur via propagation, we first need an active site. And these active sites can also terminate and do much more. Anyway, quite a difference again with respect to step growth. And a further difference with respect to step growth is that in chain growth, very long polymer chains may be already observed at low conversion. Let me pull up again the features of step growth, just in case you want to pause the video at this point to look at them together. But now let's move on towards making our first step into modeling these type of polymerizations, at least with respect to the formalism for the main reaction describing growth. And let us start with step growth. Now, we said that things in step growth begin with the reaction between two monomers, forming a dimer. It could be an equilibrium limited reaction. In some cases, we are considering such a case here. We also know that in step growth, any species may react with any other. So, for instance, a trimer and a monomer could form a tetramer. Okay, so a chain of 4 monomer units. How do we formalize these reactions? Well, as usual, we need to identify the reagents participating. So the monomer I could call here in this case a chain of length 1, so I call it P1 plus P1, and I say that this is in equilibrium with a P2 chain, where 2 represents the number of monomers belonging to this chain, and R is our group, which a small molecule which is released during this equilibrium reaction. I could do the same for the trimer and the monomer that together form a tetramer, and I would use then P3 for the trimer for the 3 repeating units, and then a P4 for the tetramer, and again P1 for the monomers. Okay, we could go on, of course, right? There are many other combinations. We could write them all, but it would be somehow cumbersome, right? Like how many other, there are many more, right? Possible reactions. We said any chain can react with any other, okay? Thankfully, we can rely on a very convenient formalism. That refers to any 2 generic polymer chains, and we will call them P of N and P of M. They together react, forming a longer chain of length N plus M. And what are these subscripts that we're using here, N and M? They're just numbers, they're integers larger or equal to 1. Okay, so any 2 chains will react with one another, releasing potentially an R group. They are at equilibrium and they form a longer chain of length N plus M, or if you prefer, consisting of N plus M monomers. Okay? A very important note here, it's a formalism, but it's important. Monomer in step growth, and I did this implicitly when we started this slide, monomer is considered as part of the polymer. Okay, so in fact, whenever I spoke of monomer, I always reported it here as a P of 1, so a polymer chain of length 1. Why is this the case? Because the monomer, it's the one that starts the reaction with no activation needed. So in fact, it is already a polymer chain, just a very short one of length 1. This is very different in chain growth. And speaking of which, let's have a look at how we can formalize chain growth. Now, at the cost of repeating myself, it's an important point, I believe. In chain growth, we typically have other reactions occurring, right, that form and destroy active sites, for instance, as opposed to step growth, where already with one reaction we can describe polymer formation. This is not the case in chain growth, but we need somehow to describe the first polymer chain. We will start here with any radical species. We'll call this a star here. The star actually indicates that this could be any type of radical, and actually this is valid even if this would be an ion, right? So to keep generality, we use the star here. So an active molecule, a star, attacks a monomer, here M, and forms a P1 star. Unlike in step growth, in chain growth, the monomer is not considered part of the polymer, since again, without activation, no polymerization can really start. So the monomer alone is truly not a polymer chain of length 1. Now, back to our formalism. Now we have our first polymer of length 1, but what happens next? Well, the active chain will grow, right? And it will attack another monomer, and so we could write here, well, P1 star plus M forms a P2 star. One more monomer? Sure thing. So a P2 star plus M gives a P3 star. Again, here we would need to write very many reactions, but again, we can use this formalism that we saw before to generalize. So we consider the generic activated polymer chain of length N, so Pn star, where again the P represents a polymer chain, the subscript N indicates the number of repeating units, and the star, the fact that it is active. This reacts with a monomer, M, again here, and forms a longer chain of length P of N plus 1, because of course we added a monomer here, still with the star that still indicates that it bears the active site. Okay? And again, N is a number, an integer number, larger or equal 1. Don't worry, because this formalism will accompany us in many of the next videos, so we will have a chance to have a look at it again, but now it's time for our recap. So we saw that polymer chains are formed via two main classes of reactions, step growth and chain growth. We saw the key differences among these two mechanisms. For instance, we saw that step growth implies a slow buildup of molecular weight and sequential steps mediated by functional groups. First, we need a buildup of oligomers, and only then higher molecular weights can be reached, as opposed to chain growth, where a polymer chain is initiated by an active species and only then grows, reaching large molecular weights or chain lengths already at small monomer conversions. We also saw some first modeling considerations. We introduced a compact formalism using a subscript to account for the chain length. This, of course, is just the beginning of our modeling journey. If you liked the video, have comments or questions, I would be very happy to hear from you. Just let me know. Bye.